This is the 9th video in a series devoted to introductory proof writing. Today we're going to look at the pigeonhole principle and combinatorial proofs. So let's start with the definition, which will lead us towards the pigeonhole principle. So given a real number x, we'd like to define this function called the floor of x, which we'll use this following notation, as the largest integer n such that n is less than or equal to x. And then as a dual to that, we'll define something called the ceiling, and we'll have similar notation, and that will be the smallest integer n such that n is bigger than or equal to x. So you can think of the floor as an elevator downstairs to the closest integer, whereas the ceiling is an elevator upstairs to the closest integer. So let's look at a couple of quick examples. So the floor of 2.3 is equal to 2. We go downstairs to 2. The floor of E is equal to 2. That's because E is 2.718. The floor of 2.99 is also equal to 2 because it's not quite equal to 3. And the floor of 2 is equal to 2. That's because if you're at an integer, by this definition, you don't have to go downstairs. Next up, the floor of -3/4 is -1 because that's downstairs from -3/4. Then the ceiling of 8.0001 is 9 because the ceiling says to go upstairs. So now let's look at the following fact, which is actually a generalization of the classic pigeonhole principle. So let's suppose we have n objects and we are to place those n objects in k boxes. Then at least one box contains the ceiling of n over k objects or more, and another box contains the floor of n over k objects or fewer. So let's do a quick example to see why that is true. So let's take 8 objects and let's place them into 3 boxes, and we're going to do it semi-randomly. So let's take this first object, we'll place it into this first box. And so let's draw this object occurring in this box. So there we've got it. Then maybe we'll take this second object and we'll place it in the third box. So there it is there. Then maybe this third object will be in this second box. And now let's keep going. This fourth object, let's put it in the third box. Let's say this fifth object goes back to the first box. And then maybe this sixth object goes into the last box. Okay, so there's my object there. And then let's say this next one, this seventh object, will go into our second box. And then finally, the last object, the eighth object, is placed into our first box. Okay, so now let's notice that this first and this third box both contain 3 objects. But how many is 3 in terms of 8 and 3? Well, it's going to be the ceiling of 8 over 3. So like I said, this contains the ceiling of 8 over 3 equals 3 objects. And we're guaranteed for something like this to happen by our fact over here. Well, we're really guaranteed for there to be a box with this many objects or more. But in this case, we have exactly this many objects. And now let's look at what we have right here. So this has 2 objects, and 2 objects is the floor of 8 over 3. So this one has the floor of 8 over 3 or 2 objects. And we're guaranteed for a box to have that many objects or fewer, again, by this portion of our fact. Okay, so now that we've investigated this fact, let's look at the classical pigeonhole principle and then do several examples. Now we're ready to look at a special case of our general fact, which is classically known as the pigeonhole principle. So let's suppose we place n objects into k boxes. Then if n is larger than k, then at least one box contains more than one object. And towards our general statement, that's because if n is bigger than k, then n over k is strictly larger than 1. So when we take the ceiling, you get something bigger than or equal to 2. And then if n is less than k, then at least one box is empty. And that's because, again, if n is less than k, then n over k is less than 1 strictly, which means when you take the floor, you get 0. Okay, so now let's look at an example. Let's suppose we have 6 distinct integers and they're between 0 and 9. Then we'd like to show that 2 of them must add to 9. Okay, so we've got 6 objects. Those 6 objects are the 6 integers, and we'd like to place them into less than 6 boxes. And so likely it'll be exactly 5 boxes, because for these introductory examples, you generally have one less box than objects, forcing 2 objects in a single box. Okay, so what might those boxes be? Well, there's a big hint built into this based off of the fact that we want 2 of them to add up to 9. So those boxes are based upon pairs of numbers that add up to 9. Okay, so let's get to it. So let's distribute our 6 integers among the boxes described as follows. So our first box will contain the numbers 0 and 9. Our second box will contain the numbers 1 and 8. Our third box, 2 and 7. Our fourth box, 3 and 6. And finally, our fifth box will contain the numbers 4 and 5. So we've got 1, 2, 3, 4, 5 boxes. We are to put 6 integers inside of these 5 boxes. So that means we're guaranteed 2 of these integers land in the same box. So let's write that down. So we are guaranteed to have 2 integers in the same box. But let's notice if those 2 integers lie in the same box, then since they are distinct, they're non-equal in the same box, which means they sum to 9. So let's write that out. These sum to 9. And that's really all there is to it. You could write this down a little bit more carefully, but I'll maybe leave that as an exercise. We'll write down a solution to the following examples, which are a little bit more complicated, more carefully, so you can use those as a guide. Okay, let's move on. Now we're going to look at a very classic example. So a version of this example generally is inside of any proofwriting book that I've seen that covers the pigeonhole principle. So let's suppose we have n plus 1 integers. I'll call them a1 up to an plus 1. And then our goal is to show that we can find 2 of those integers so that their sum or their difference is a multiple of 2n. So I've written that carefully as show that we can find I not equal to j between 1 and n plus 1 such that ai minus aj or ai plus aj is a multiple of 2n. Okay, so how are we going to do this? Now this being a multiple of 2n gives us motivation to divide each of these numbers by 2n and keep the remainder. And this may not seem super obvious at the moment, but as you'll see moving forward, anytime we're trying to show something as a multiple of something else, it's common to look at the remainder when dividing by that number. Okay, so anyway, let's get to it. So like I said, we want to divide each of these AIs by 2n and keep the remainder. So let's define a new set of numbers. So for all 1 less than or equal to I less than or equal to 2n, let's define Ri by the following equation. So we have AI equals 2n times Qi plus Ri, where Ri comes from the set between 0 and 2n, but it's not allowed to be 2n. Okay, so this is something called the division algorithm, which we talked about in a previous video. So let's just point out here, this is the remainder, or these are the remainders of the AI when divided by 2n. So what's nice about this is it takes a set of integers that can be really of any size, and it restricts them down to a set of integers between 0 and 2n. So that's pretty nice. Okay, so now we're going to look at 2 cases, 2 disjoint cases, I should say. So that first case will be the following. So let's suppose we have I not equal to j such that Ri is equal to Rj. Okay, nice. So that's definitely a possibility. And you might say, well, this is a super restrictive possibility, and maybe it is. But we'll cover all other possibilities with case 2, which, as we'll see, will be essentially not case 1. Okay, so now what we'll do is either look at the sum or the difference. And maybe you'd like to play with it, but I think looking at the difference is maybe the obvious thing to do here. So I'll write it like this. So now let's note that AI minus AJ in this case is equal to, well, we'll write AI and AJ using this formula right here, which we've derived for them. So we have 2nqi plus ri, and then minus 2nqj plus rj. But by our assumption, Ri and Rj are the same. So that means when we take Ri minus Rj, those cancel. And thus we can factor a 2n out of what's left over, and we have 2n times qi minus qj. So what does that mean? So we've got qi minus qj is 2n times something. So that means AI minus AJ is a multiple of 2n. And now that'll bring us to our second case. So we just looked at the first case of this proof, and now we're ready to look at the second case. Let's recall the first case was there is an I not equal to j such that Ri equals Rj. We haven't used the pigeonhole principle yet, so hopefully we use that in this second case. But this second case will be exactly not the condition on the first case. But luckily, we've done some work in the past of negating statements. So let's negate the setup of the first case. So we have this existential quantifier. There exists I not equal to j, so that's going to turn into a universal quantifier. So for all I not equal to j, we have this statement is not true. So Ri is not equal to Rj. But now we've got n plus 1 numbers, R1 through Rn plus 1, that we'd like to put into n boxes, or n or less boxes, to use the pigeonhole principle. So let's figure out what those boxes are. So let's start by, we'll distribute the n plus 1 numbers. Let's see, R1, R2, all the way up to Rn plus 1 into the following boxes. And those boxes are going to be all pairs of remainders after dividing by 2n that add up to 2n. So this is taking motivation from that previous example that we did. Okay, so one pair would be 0 and 2n. And I guess we're saying that we need to do summing here because we did differencing, or we did subtraction in the first case. And so that would be a pair of remainders that add up to 2n. And then next we would have 1 and 2n minus 1. And then I'm going to put a general one in here, k and 2n minus k. And then the next to last one would be n minus 1 and n plus 1. And then the final one would be n and n. But there's something that's a little bit fishy with these boxes. First of all, since these Ri's are remainders after dividing by 2n, we know they must be strictly less than 2n. They're between 0 and 2n. We can include 0, but we cannot include 2n. So that means this is an impossibility. But that's actually not a huge deal. What is a huge deal is that we have n plus 1 total boxes at the moment. But we've got n plus 1 objects, so that doesn't help us out at all. So what we'd like to do is somehow throw away one of those boxes. And indeed we can. We can throw away this last box where both of the remainders are equal to n, and that's because we have this assumption right here that the remainders are different. So that means we can scrub away that possibility, and we in fact have n boxes. So we've got n plus 1 objects to put into n boxes. That means 2 of those objects are guaranteed to be in the same box. Okay, so let's write that down a little bit more carefully. So we have I, J, and K such that Ri and Rj come from the box, or the set it would be, K and 2n minus K. And here I guess I should say I is not equal to J. Okay, so that would be like Ri and Rj coming from the same box. Okay, but now one of these is going to be K and one of these is going to be 2n minus K. So maybe let's just, without loss of generality, assume that Ri is equal to K and Rj is equal to 2n minus K. Again, they cannot be the same by our assumption right here. Okay, so that's good. Now, since we looked at the difference before, in this case, we will look at the sum. So let's look at AI plus AJ. So that's going to be 2n times QI plus RI. Let's recall that RI is equal to K by our assumption. And then we'll have plus 2n QJ plus RJ, which is 2n minus K by our assumption. But now we get some nice simplification. This K here cancels with this K here. And then everything else is a multiple of 2n, making the sum a multiple of 2n. And we can explicitly write it as the following multiple of 2n. We have 2n times qi plus qj, and then plus 1, from factoring the 2n out of this term right here. So in the end, we have AI plus AJ is a multiple of 2n. So let's see, these two cases are disjoint and they make up all possibilities. In the first case, we saw that the difference of these two numbers was a multiple of 2n. In the second case, we saw that the sum of two of the numbers was a multiple of 2n. So that proves this claim up here, which was our, maybe like I said, very classic example. Okay, let's do another. Now we have what is one of my newly favorite examples for the pigeonhole principle. So let's see the setup. Let's suppose we have 101 natural numbers whose sum is 300, and we'll place all of those numbers on a circle. And then our goal is to show that we can find a consecutive sequence of these numbers whose sum is 200. Okay, so I've laid out a picture here just to get us started. So I have my circle, and I have my 101 numbers, which I have noted as A1, A2, A3, so on and so forth, up to A101. So since they're on a circle, we have A101 next to A1. That will be important moving forward. So let's see the proof here. So since we're trying to find a consecutive sequence whose sum is 200, that motivates us to look at the partial sums. So let's do that. And we'll define the sequence of partial sums. So let's consider the sequence of partial sums, which I'll write as SM, and that's going to be A1 plus A2 ending at AM. And we can define these for all m between 1 and 101. So let's, for instance, notice that S1 is equal to A1, S2 is equal to A1 plus A2, and finally up to S101 is the sum of all of these numbers, which we are assuming to be 300. So S101 is, in fact, 300. That'll be a good bit of information. So now let's take these 101 numbers and put them in 100 boxes. We just have to figure out which boxes to put them in or how to define those boxes. But the definition of those boxes is hinted towards by the fact that we have a 300 here and a 200 here. And what's common about 300 and 200? Well, they're both multiples of 100. They both end in 0, 0. So I think that gives us some motivation to define the boxes by the final 2 digits of a number. And in fact, there are 100 possibilities for the final 2 digits of a number. We've got 100 numbers, so that means we've got one more possibility of numbers than possibility of final digits. So that's really good. Okay, so now let's put these 101 numbers and let's just write those numbers out, S1, S2, up to S101, into the 100 boxes, which are defined as, maybe, like I said, by the final 2 digits. So I'll write them like this. So my first box I'll write as star 00. We don't care what it starts with, but it ends with 00. The next one will be star 01. The next one will be star 02. We would end with star 99. So 2 of these must be in the same box. So what that means is that we have an SN and an SN plus K that are in the same box, but being in the same box means they are of the form star AB. In other words, they end in the same digit. Now you might say, well, why did I write SN and SN plus K instead of like SN and S some other index? Well, I think it's helpful here to notice that these two will have different indices. One of the indices will be larger, so it kind of makes sense to write the larger one as an extension of the smaller one. Okay, great. Now I'd like to make a really quick observation, which I think is pretty obvious here, and that is SN plus K is strictly bigger than SN. And that's because we have natural numbers we're adding together here, and SN plus K is further in this sequence of partial sums. Now let's look at the difference of SN plus K and SN. So let's write it like this. So let's notice that SN plus K minus SN is of the form star 00. And that's because they end in the same 2 digits. But since they end in the same 2 digits, when we take their difference will end in 00. But that actually restricts the possible values. So they cannot be the same, so they can't just be equal to 0. And we know that for sure because SN plus K is strictly bigger than SN. But they cannot be equal to 300 or larger than 300. They can't be bigger than or equal to 300 because the sum of all of the numbers is 300. Well, that only leaves 2 possibilities. But that means that this difference, SN plus K minus SN, comes from the set 100 or 200. But that's going to break us down into 2 cases. Well, if they're equal to 100 or if they're equal to 200. Let's look at this first case where they're equal to 200. That one's actually easier. Okay, so case number 1, which is SN plus K minus SN equals to 200. But we could rewrite that as 200 equals SN plus K minus SN, but by the partial sum definition of these S's, that'll end up giving us AN plus 1 plus AN plus 2 plus all the way up to AN plus K. In other words, we have consecutive numbers along this circle that add up to 200. And I could draw them on the circle like this. Maybe AN is right here, AN plus 1 is right here, all the way up to AN plus K is right here, and then maybe the next one might be important also, AN plus K plus 1. So here what we did is we added from AN plus 1 up to AN plus K, and we got the number 200. But of course, that's for this first case where they sum to 200. Now we need to look at the second case where they sum to 100. So we just looked at the first case, which is when SN plus K minus SN was equal to 200. And in that case, we got this string of terms summed together, starting at AN plus 1, ending at AN plus K equaled 200, which showed that we had the right kind of consecutive sequence. But now we're going to look at the other case and show that we can get a consecutive sequence in that case as well. But let's notice if SN plus K minus SN equals 100, then by what we saw previously, that means that AN plus 1 plus AN plus 2 ending at AN plus K equals 100. In other words, this sum from here to here is equal to 100. But if that sum from there to there is equal to 100 and the sum around the whole circle is equal to 300, that means the sum of the remaining stuff from here all the way around to here is equal to 200. Again, because simply 300 minus 100 is equal to 200. So we can now put that into words as follows. So we'll observe that 200 is the same thing as 300 minus 100. So I think that's pretty obvious. We can write 300 as A1 plus A2 ending at A101. And then we can write this 100 as this sum right here. So we have AN plus 1 ending at AN plus K. Great. But now performing that, we get the following sum. I'll maybe start it right here and then loop around. So we'll have AN plus K plus 1 added all the way up to A101. So that would be from here to here. And then plus A1 all the way up to AN. So we have 200 is equal to that, but that's another consecutive sum of terms along this circle. So either way you look at it, we are able to get a consecutive sequence along this circle whose sum is 200. Okay, let's look at another one. So for our last pigeonhole principle example, it's kind of geometric. I think that's nice. So let's say 9 points are placed in an isosceles right triangle with side length 1. So I've drawn the triangle here. We've like I said, we've got an isosceles right triangle, side length is 1. Then our goal is to show that 3 of them form a triangle whose area is at most 1/8. So let's maybe notice that the area of this entire triangle is 1/2. That's because it's 1/2 base times height. So that gives us motivation to split this up into 4 pieces. 4 pieces because 1/8 is 1/4 of 1/2. So furthermore, we hope that we can split this into 4 nice pieces. So let's see if we can split it into 4 pieces, all of which are isosceles right triangles. And in fact, we can. Let's split each of these into half. So we'll split each of these legs into half, and then we'll make line segments connecting them like this to the hypotenuse. Now let's note that since those are split in half, we have a length of a half here, a length of a half here, this is a length of a half, and this is a length of a half. So this triangle right here that I'm shading in brown has area 1/8, and so does this one right here that I'm leaving unshaded. But that didn't split this into 4 pieces that are the same. We've got 2 triangles and 1 square. But we can split that square into 2 triangles as well. And maybe we'll split it into 2 triangles like this, although we could split it across the other diagonal as well. And now let's notice we have split this into 4 equal triangles that are all isosceles triangles with side length 1/2. Then furthermore, let's notice that we've got 4 boxes here, if you will. The boxes are triangles, and we're trying to put 9 points into each of those 4 boxes. We're guaranteed to have 3 points end up in one of these boxes. But those 3 points will make a triangle, and that triangle can't at most have area of the entire triangle that it lives within, but the entire area of the triangle that it lives within is 1/8. So that's a sketch of how to do this. Now let's write it out. So maybe we would use the following words. Let's partition the triangle into 4 similar isosceles right triangles with side length 1/2 per the diagram. I think it's fair to say that we're explaining what's going on with this diagram over here. Then next, so of the 9 points, 3 are guaranteed by the pigeonhole principle, but maybe we don't need to say by the pigeonhole principle explicitly, well, especially since I'm saying it out loud here. So of the 9 points, 3 are guaranteed to be placed in the same subtriangle. So by subtriangle, I mean either this one right here, this one right here, this one right here, or this one right here. Okay, well, let's also maybe like give a name to those points. So let's call them A, B, C. Great. So again, that's by the pigeonhole principle. And now we can maybe note the following. So the area of triangle ABC is less than the area of the subtriangle. The subtriangle is an isosceles right triangle with side length 1/2. And that has an area of 1/8. But now we've done exactly what we wanted to. We found 3 points that form a triangle whose area is at most 1/8. Okay, so now let's move on to some combinatorial proofs. So to put it simply, a combinatorial proof involves showing two expressions are equal by showing they are answers to the same counting problem. So we've done this one in a previous video, but I thought I'd do it again just because now we're talking about combinatorial proofs, officially. Okay, so let's show for all natural numbers n and k, where k lies between 1 and n, we have n plus 1 choose k is equal to n choose k minus 1 plus n choose k. And so let's quickly recall that n plus 1 choose k is equal to the number of k element subsets of an n plus 1 element set. But we might as well write down an explicit n plus 1 element set. And I'll write 0, 1, 2, 3, ending at n. So I think that clearly has n plus 1 elements because we are including 0 here. Okay, so that's the left-hand side of this proposed equation. Now we'd like to count the number of k element subsets of 0 to n, another way to achieve the right-hand side. And we can do it as follows. So let's suppose that A is a subset of 0, 1 up to n, where the cardinality of A equals k. So in other words, it's a k element subset of our set right here. And now let's notice that there are two possibilities for A. So I'll write those down as cases. So case number 1 and case number 2. So case number 1 is that 0 is an element of A. Okay, well, so if 0 is an element of A, then we can write A as follows. It's equal to the singleton 0 disjoint union. So I'm going to introduce some notation here. We have a union with a dot there. That means disjoint union, which means these two elements will not overlap. So it'll be disjoint union A prime, where A prime is a subset of 1, 2 up to k, up to n. So it's a subset of 1 up to n. So in fact, what we're really just doing here is using the fact that 0 is an element of A, we're pulling 0 out of A, and we're seeing what's left over. So let's also note that the size of A prime now is k minus 1. And we can see that because we've taken a single element out of A prime. Okay, so that's good. So how many such A prime are there? Well, it's really easy to count because all we have to do is count k minus 1 element subsets of an n element set. So there are n choose k minus 1 such A prime. But the A prime completely determine the A in this case because we're assuming that A contains 0. Thus A, in this case when A contains 0. Okay, so let's just reiterate what we've done right here. We have A is a subset of 0 to n. In this first case, we have 0 as an element of A, which is definitely a possibility. And then we've shown that there are n choose k minus 1 such A's. So there are n choose k minus 1 subsets that contain 0. Okay, let's look at the next case. And the next case will be, well, what happens if A is not containing 0? So 0 is not an element of A. But if 0 is not an element of A, then that means that A is just plainly a subset of 1 to n. Okay, but how many elements are in A? Well, there are k elements in A. That's kind of our assumption from the very beginning. Okay, but how many such A's are there in this case? Well, that's easy to count as well, because A is a k-element subset of an n-element set. So there are n choose k such A's. Great. But this covers all different cases. So if we have a subset of 0 to n, then it either contains 0 or it does not contain 0. In the case that it contains 0, there are n choose k minus 1 of them. In the case that it does not contain 0, there are n choose k of them. So we've counted the number of k-element subsets of this a different way. So by definition, it's equal to n plus 1 choose k, but by this other counting procedure, it's equal to the sum of these two. So putting this all together, we have n plus 1 choose k is equal to n choose k minus 1 from case 1 plus n choose k from case 2. Okay, let's do another. Okay, so for our next one, we'll show for all natural numbers n and k, where k is between 0 and n. I guess that really makes k perhaps not a natural number, but a non-negative integer, but we'll let it slide in this case. So with that setup, we have n choose k is equal to n choose n minus k. So we're gonna note that n choose k is the number of subsets of 1 to n with k elements. So maybe we'll start with a subset from the set containing 1 up to n with k elements. So that's what I'll write down here. Suppose we have A, which is the subset of 1 to n, where the number of elements of A is k. Okay, now let's notice that we have the number of elements of A complement is equal to n minus k, because it's the number of elements of the universal set, which is understood to be 1 to n in this case, minus the number of elements of A. So I think we saw this in a previous video, or this kind of formula in a previous video. So we have n minus k. So that defines a unique pairing. So I'll write this down. So we have a unique pairing of sets A with their complement A complement. Which means if there's a certain number of possible sets of the form A, then there are a certain number of possible sets of the form A complement. So how many sets are there of the form A? Well, the only thing restricting A is that it must have k elements. So that means the possible types of sets A here are n choose k. But then how many possible sets are there like A complement? Well, the only thing governing A complement is that it has n minus k elements. So how many sets are there with n minus k elements? Well, there are n choose n minus k. And again, since this pairing is unique, we must have equality between these two choices of types of sets. Okay, we're going to do one more. So for our final example, we'll look at a nice combinatorial proof of a fairly famous sum identity. And that says the sum as k goes from 0 to n of n choose k squared is 2n choose n. Sometimes this is known as a central binomial coefficient, just by the way. So let's maybe look at a little example of this real quick, although we won't work out all of the details. Let's say we have n equals 4. So that means we'll have 4 choose 0 squared plus 4 choose 1 squared plus up to 4 choose 4 squared must be equal to 8 choose 4. Now, you can check that that works out if you'd like to, but really there's kind of no point because we're about to prove it in general. So I think a good first strategy is to look at one side of the equation, which we can easily write down what it means combinatorially, and show that the other side of the equation also counts that type of object. Okay, so let's do that as follows. So let's note that 2n choose n equals the number of n element subsets of a 2n element set, which I'll call 1, 2, up to 2n. Okay, so that's a good first observation to make. Then let's notice that the parts of this sum are counting the number of k element subsets of an n element set. and we're squaring them, so I think that motivates us to split this 2n element set into 2 n element sets. So let's maybe do that with the following observation. So if x is a subset of 1, 2, up to 2n, with the number of elements in x is equal to n, then we can write x as the disjoint union of a, b. So I'm using that notation again, where a is a subset of 1 up to n, where the number of elements in a is k, and b is a subset of n plus 1 up to 2n, where again b has n minus k elements. Okay, so I think this is looking good, and I think that motivates our final, what I'll call calculation. So let's do it here. We have 2n choose n is equal to number of n element subsets of 1 up to n. Okay, let's maybe put a yellow box around that. But that'll be equal to the sum as k goes from 0 to n of the number of k element subsets of 1 to n. That's like deciding the number of ways to choose this subset A, and then times the number of n minus k element subsets of n plus 1 to 2n. That's like choosing the number of ways that we can pick this subset B. Great, and then of course we're taking a sum here by the sum principle. So we would sum over where we had a 0 element subset A and an n element subset B, all the way up to having an n element subset A and a 0 element subset B. Okay, but now we can count each of these orange and red boxes using like the definition of the binomial coefficient. This gives us the sum as k goes from 0 up to n of n choose k times n choose n minus k. But by our previous example, we know that n choose n minus k is the same thing as n choose k. So in the end, we get n choose k times itself, or n choose k squared. Okay, that's good. Now I'm going to leave you with some warm-ups. So now I've got 2 warm-up problems for you. So the first is to, well, suppose you're in a class of 17 students. So that includes yourself. Then you'd like to show that at least 3 of you were born on the same day of the week. So this is like a pigeonhole principle problem. And then next, let's find a combinatorial proof of the famous identity for triangular numbers. That says 1 plus 2 plus 3 ending at n is n plus 1 choose 2. So there are many different ways to prove this, but here we want to look for a combinatorial proof. And that's a good place to stop.